The following video has these questions in it. So make sure to pay attention to the timestamp, and whichever question catches your interest, or if you want to look at all of the questions, make sure to use the timestamps accordingly. It will be on the progress bar of the video. Let's get straight into the introduction. So this video goes under, I was going to say over actually, but kind of under would have been a funny way to say it. This video actually goes over the area between the curves. Okay, so with the area between curves, right, how are we going to go about this? Let's just understand what is happening. So with this content over here, let's say that we have a Cartesian plane, right? Let's just say it's a first quadrant Cartesian plane that we have here, and then we have some function. Let's say there's a function like here, right? That's a function. It can be a function. It is. And then let's say that we have another function. Now let's say the function is a little bit lower than that, right? Now what are we going to be doing from here? Well, we kind of want, our goal for this whole video is to be able to easily find the area between certain curves. So something like between this, for example, okay, because it's between. But how do we actually go about doing this? Now, first of all, let's get rid of the other function, right? And let's say that we just wanted to find the area under the curve. Now, we know that we would just find this area here. Okay. So we're actually trying to find the area, but note that what we're actually doing is we are finding the area between the function, which we can suppose f, right? Like so, and this one here, which is the x-axis, right, which is actually our y equals to 0 line. Okay, so we're actually doing that, and note that it's actually the difference between this function's area and this line's area, and note that the line, the x-axis, doesn't actually have an area. It's just 0. It's a straight line and there's no gap between it. So how do we notate this? Now we can actually notate it as follows. We can say that the area, right, is actually equal to the integral of the function minus 0, because we found the difference between the two in a certain interval a to b. Let's say, for example, a was here and b would be somewhere here. Okay, so it'll look something like this. And then let's make it a little bit more neat so that it kind of looks like we're actually answering the question. Okay, so something like that. So this is how we actually make up our function, and I can see on the screen it's a little bit out of the frame, so let's move a little bit downwards here, and hey, there we go. What do we have? We have this. Okay, great stuff. But now if we wanted to actually find the area between the two curves, this is what we're going to do. So instead of saying 0, and also note that if we were to just simplify it, right, we would just get rid of the 0, and then therefore we actually have the integral of the function itself. Does that make sense? So it's actually the net area in this case. But what if we wanted to add another curve into this? Now this is where we have to take everything else into consideration. So let's say we have some funny looking function here, but we want to still use it in the interval that we are provided with, a to b. So in order for us to do that, note that we have an area underneath the function of f, right? And let's suppose that this function here is actually g. Okay, it's g. And we need to find the area first under the function f of x. Okay, so it'll be this whole area, including that whole, the whole curve that we just introduced here. Now, we need to take that whole area, right, you can see represented here, and we need to actually subtract it by this area underneath the other curve. And note that that difference just gives us the gap here. If you to do it by yourself, you'll even notice it. Okay, so therefore, when we subtract this area, right, let's say this with respect to x, minus the integral in that same interval of g of x, okay, let me go to this arrow. What we are actually saying is that's going to be this area. It's going to be this area right here. Okay. So obviously what we can do, we can actually rewrite this now as the area is equal to the integral from a to b, right? And we can actually just use the property, because they're in the same interval, we can just put them in the same integrand, such that this will be f of x minus g of x dx. Okay, so there's our area between the curve. And then also something to kind of consider is that you would normally first state the top. So note how this would be the top function, and you would minus it by the bottom function. Okay, so that's normally how it works. So you wouldn't just minus any of them. You can't just randomly say g of x minus f of x. It has to have a reason for why you are subtracting them to find the difference. If you just swap the g of x around with the f of x, then it's not going to give you the same area, because you're not really finding the area between the curve. Okay, so let's actually get into the examples and understand what is actually happening here. So here's our first example, and this is a certain type of question. There's actually two ways they can ask this question, and this is the first type, and we're going to just do two examples on this. So the first question here is, find the area between two curves, right? The two curves given in the given interval. So they are saying they're giving an interval for us to find the area. So which means we just need to find the area in the interval, or the closed interval, 0 to 2. And they give us two functions. They give us y equals 2x, and they also give us y equals 2x squared. So what we need to do is we need to sketch those functions, and then we need to find out where they kind of intersect, right? So we can find the area between a region, between the intersection points, and also where until where it ends. And you'll understand that point when we actually go further. So, but the thing is, we can draw the graphs. We know how to draw this graph, right? It's a linear function, and this one is a parabola. But how do we know how to specifically draw it? Well, the first thing we really need to do is to find the points of intersection. We need to know where they intersect first, so we can actually proper illustrate these functions. So what we're going to do is we're going to say points of intersection, right? We're going to say the points of intersection. And what is the point of intersection? It's where the two functions meet at the same point, where they are equal to each other, where the y values are equal to each other and the x values are equal to each other. So where they share the same input and output value. So therefore, we're going to take this function and we're going to make it equal to this function. And note it's also notated by y is equal to. So they're both the same. So therefore, we're going to say 2x is equal to 2x squared. And then from here, we can kind of simplify it for ourselves. We can't divide both sides by x, but we can divide both sides by 2. So that all of these can cancel. And then what we are left with is we are left with x is equal to x squared. Okay? And we can't divide both sides by x, but we can take the x over on the other side, or we can minus both sides by x, such that we're left with 0 is equal to x squared minus x. And then we can take out a common factor of x, and we will be left with 0 is equal to x into x minus 1. And therefore, what we have is going to be x is equal to either 0, right, because that's in the bracket, or x is also equal to 1. So there we go. We just got our 2 points for the function. Now it should be pretty straightforward to do, right? We can actually just draw the function. But there's also an issue, right? We know that clearly the functions meet at the origin point, right? Because they intersect at x equals to 0, both of them. And clearly there is no vertical shifts in any of these functions. But how do we know for x equals to 1 though? So for x equals to 1, we can actually show that, let's plug it into one of the functions. Let's do y equals 2x. For y equals 2x, when we plug in x equals to 1, we will have 2 times 1, which is just equal to 2. So therefore the y value that they also intersect at is equal to 2. And therefore, we can actually just take make our own Cartesian plane here, and then we can sketch the following functions, right? So we have a y and an x-axis. I normally like to draw this so that it's clearly indicated. And then from here, we can just draw them. Well, we have y equals 2x, but let's just put down the numbers on the system first. So we know that they intersect at the origin, which is at 0. And x equals 1 is also a point. So let's put it somewhere here. And then also there's a value of y equals to 2. So let's put it somewhere high up here, such that they actually intersect at x equals 1 and y equals to 2, given by this substitution here. So therefore, we are going to meet it over here, like so. It's not very straight. I'm sorry about that. And then we have 2 points of intersection, which is at the origin point and the coordinates 1 and 2. Not going to draw that down. We're not going to draw that. So let's just sketch the y equals 2x. We know what it looks like. It's a linear function, and it's an increasing function because of its slope. It has a positive slope. So it looks something like this. And that would be y equals to 2x. And then we're going to draw our y equals to 2x squared, which would look something like this. Okay. Or let's kind of draw it something like this. Or like this. I'm so good at drawing, guys. And then here we have that. So y is equal to 2x squared. Okay, great. So with my beautiful drawing right now, we are going to actually find the area between what interval? 0 to 2. So we note that there's actually a region here between 0 and 1, right? But we don't have 0 and 2. So we're just going to actually plot a specific point, and I'm going to extend this line here. Okay? So that when we find, let's suppose that 2 is somewhere here, such that we need to find out what the y value is going to be when y is equal to 2. So therefore, what we're actually going to say is where x is equal to 2, we're going to have y is equal to 4, if that makes sense. And then therefore, it meets at the y value of 4. Let me put the y here. Okay, so I just extended it a little bit. And therefore, we are actually going to have some area like this. Okay, something like that, all the way until x equals to 2. And there we go. But how are we going to notate this? Now we know that to find the area between the curves, it's going to be the integral of top minus bottom with respect to its bound, which is in terms of x. So therefore, we already have one piece of area. But what about this part over here that's isolated from the other area? Well, this is the point where we're actually going to add this area here. We're going to add this area with that area over here, such that we're actually going to have two integrals in different bounds. So this is what it's going to look like. This is going to indicate to us, and I'm just going to write it down here, equals 2x. The area is going to be equal to the integral from 0 to 1, right? Because it's this bound over here from 0 to 1, of which function is above. It's the dark one, right? The dark is going to be y equals 2x. So we're going to write 2x over here. Okay? And then it's going to minus the other function, which is 2x squared, which is lower than that function. And now we're going to add this with another area within the interval of 1 to 2. And then we're going to have the top minus the bottom. The top this time is going to be the red one. The red one is actually higher. So therefore, we're going to have 2x squared, which is the red one, minus 2x. Also, I forgot to add the dx. My apologies. And then there we go, dx. So therefore, we have just done it like that. Okay. So here, it's going to be this area here plus this area here, which gives us our combined area. Okay. And now we just have to integrate. Okay. So therefore, the area is just going to be equal to, once we integrate, right, we're going to have the following. So I'm going to take out 2 as a common factor, and then we're going to be left with x squared over 2 minus, and then we're going to be left with x cubed over 3. Note how I'm just taking the integral of 2x, or sorry, just x and x squared, because I took out the 2 as a common factor already. And then we obviously have it within the bound of x equals to 0 and x equals to 1. Plus, we also take out the 2 as a common factor over here, such that we just integrate these two separately. So it'll be x cubed over 3 minus, and it'll be x squared over 2. And then we have it within the bound of x equals to 1 and x equals to 2. Okay. And then from here, what are we going to do? We are just going to evaluate. we're going to say that the area is actually just going to be equal to, and when we're just going to evaluate, we're going to disregard x equals to 0. Why are we doing that? Because if we plug in x equals to 0, it's just going to give us an answer of 0. So therefore, we only need to consider x equals to 1, such that we are left with 2 into 1 over 2 minus 1 over 3. And then we're going to add this with the other part, which is going to be, so let me just kind of move this a little bit to the side because I'm kind of running out of space here. And we're going to have 2 into, and here we need to actually consider both x equals to 2 and x equals to 1. So therefore we are left with, we're going to do the substitutions. It'll be 8 over 3 minus, it'll be 4 over 2. Note how I'm just already squaring them. Okay. And this would be, and I'll put a bracket here actually because it looks better. And this will be minus, I'll just write it here. And we're going to have, when we plug in 1, we're going to have 1 over 3 minus 1 over 2. And then we close the bracket. And if you were to plug this all in your calculator, or if you just evaluated by yourself, you would get an area of 2. And there's the final answer for the area between the two curves, within the interval of 0 to 2. Now, you can end off with square units, but you don't have to. So that's the answer of this one. Let's move on to the next example, and we'll see the flow to answering all these questions. Okay, so this is a little bit more different. We're working with trig functions. So we have y, so it's the same type of question between the given interval. We have from 0 to pi over 2. So now we're working with radians, and we know we're working with trigonometry. Y equals to sine of 2x, and y equals to cosine of x. Now remember this forever and ever until you finish integration forever. You will never, trust me. Here we need to find the points of intersection first. Before we can draw the graph, before we know what to draw, we need to first know what are the points of intersection. Okay? And then also, once we know that information, we can start drawing the graph because it will make it easier for ourselves to actually draw them where they intersect at those points. Does that make sense? Instead of just guessing wherever and then it looks weirdly out of scale or whatever. Some lecturers don't mind it, but some lecturers are like, yay, you need to have nice scale. I don't know why they do that. But anyway, points of intersection. We are basically saying where the two functions are equal to each other. Okay. Because of space-wise, I'm not going to write down the words. So we're going to have where sine, I did not write that properly. We're going to have where sine of 2x is equal to cosine of x. Okay. And then what we're going to do here, we know that sine of 2x can actually be rewritten as 2 times sine x times cosine x, which is equal to cosine x. Okay. And from here, what are we going to do? We are not going to divide both sides by cosine x, because if we divide both sides by cosine x, it could be equal to 0 in that interval, or just anywhere else. It could be equal to 0. So it would be unnecessary to even divide both sides by cosine x. So what we can actually do is we can take cosine x over to the other side, or we can minus both sides by cosine x, such that we are left with 2 sine x times cosine x minus cosine x is equal to 0. Okay? And then from here, we can actually just take out a common factor, which is cosine of x. And therefore, what we're left with is cosine x, let's write it a little bit better, multiplied by, then we're going to be left with 2 sine x minus 1 when we took out the common factor. And note that we have two brackets now that is equal to 0. So we can actually just find our roots, which is going to be cosine x is equal to 0, or 2 sine, or I'm going to write it just like this, sine of x is equal to a half. I'm sure you know how I got this, just normal algebra. Okay. So from here, we kind of need to find the general solution. That's where we are leading to. So we kind of need to arc both sides by cosine x, or just by cosine, such that we're left with the reference angle right? So I can write that a little bit neater. The reference angle is just going to be equal to arc cosine of 0. Arc cosine of 0 is going to be equal to pi over 2. That's what it gives you on the calculator. Or if you just use the graph. Or we have another reference angle for sine, which is just going to be equal to arc sine of a half, which is just going to give you an answer of pi over 6. Okay. So from here, we're not actually done. We need solutions, right? We do need solutions. So therefore, in order for us to find the solutions, we can actually do the following. So we can say here, and I'm going to write it down here somewhere. So here, I'm going to say that for the x ref of pi over 2, we know that we can say this is the same as x is equal to plus minus pi over 2, using the cosine rule for general solutions. And this is going to be adding 2 pi k, where k is actually an element of integers. So that's the first one. So I should have actually just labeled it number 1. So I should have actually just, this can be labeled number 1, this is labeled number 2, so here we go, here's number 1. For number 2, right, we're going to have x is equal to, now for sine, normally we use the quadrant rule, where we have quadrant 1. Note that sine is actually positive, right? Sine is positive because it's positive a half. So therefore we'll be working with quadrant 1 and quadrant 2, where sine is positive. But note that the interval that we're working with is x is between 0 and pi over 2. So therefore we'll only be working with 0 and pi over 2, where we'll just be left with the reference angle. So therefore, if we were just to write this down, we'll just have x is equal to pi over 6 plus 2 pi k, and then we're going to have k is the element of integers. Write that a little bit better. I'm going to get rid of this. So there's our solutions. Okay. So those are our solutions right now that we have. And we can actually just get going to sketch the graph. So I'm going to make this a little bit neater, and you'll see what's happening now. Okay, so let's now sketch the graph. So let's look at our Cartesian plane here, right? I'm just going to draw in the middle for now. Don't worry, I can move things. It'll look much better. And note how we're not really going to be focusing in the negative interval. So we can actually just look at this part of the interval. And then note that now we're going to be working with the y-axis and the x-axis. I'm doing this because of calculus 3, and it's out of, I can see it's out of frame. I apologize about that. So let me kind of move it into frame. There we go. Great. So now it's in frame, according to my OBS. And from here, well, which one is better to draw? Let's first draw cosine x. So cosine x is actually just simple, right? We have it starting from 1, so y equals to 1, and then it just goes all, and it has a minimum of negative 1. So it would look something like this. Something like that. And then it ends at 2 pi. And then it has a point here, which is just going to be pi. This is going to be pi over 2. Draw my pi over 2 here. And this one is going to be 3 pi over 2, right? This point here. Okay. And now we can draw a sine of 2x. But note that because we have the 2 over here, it kind of cuts our period in half. The standard period of sine is 3, no, that's degrees. It's 2 pi. So 2 pi divided by 2, right? So 2 pi divided by 2 just gives us pi. And then from here, our period, our new period is just pi. Okay, so therefore it'll make a full cycle of pi. And everything is cut in half. So it'll look something like this. It would start here, and it would look something like this. So it would be like so. No, I don't think it looks like that. It looks something like this. Alright, don't mind that. Nothing happened, trust me. It's your fault. So we have something like this. Okay, cool. So roughly something like that we have. And then it would have some type of it would have an area between here. Note how there's actually area and here, and also somewhere here. I know you can't see it properly, but there's area here. Okay, according to my amazing graph, obviously, because I'm really good at drawing. But now remember, what are we actually trying to find? What's the interval from 0 to pi over 2? So we're actually going to look at this area here, this blue sections here. So this area here and that area over there. And we're going to add them together to get the net area that we are looking for in the interval. Okay. But remember, we found the points of intersection. We found the point of intersection over here by x equals to plus minus pi over 2, but we're only going to focus on the positive version because we're only working with a positive interval. So therefore, we are going to be focusing on this intersection point here, and the other intersection point, pi over 6, is actually smaller than pi over 2, which it should be somewhere here. So this is pi over 6. So therefore, we have it in the interval from x equals to 0 until pi over 6, and then we have it in the interval from pi over 6 until pi over 2. And that's how our area is going to be laid out. So let's look at this. So if we want to find the area, we're going to say area is equal to the integral between which interval? Remember, we said the first interval is between 0 and pi over 6. Okay, which is this interval here. And which function is higher than the other? Well, the reason why I did it in different colors is to say that the black one here is higher than the red one over here. So therefore, we can say that the black one, which is cosine of x, right? So you should actually rather do something like this. You should actually label it. Y equals to cosine x. And then here, this is going to be y is equal to sine of 2x. Okay, so now you can actually clearly see. Because cosine x is higher than sine 2x, we're going to write it first. So it's cosine of x minus sine of 2x. Okay, you can see there's a clear pattern going on here. And we're going to add it with the other area, which is between pi over 6 and it's pi over 2. Okay, and the integrand would be, note that red is now higher than the black one in terms of y values or output values. So therefore the red comes first, which is sine of 2x minus cosine of x. And then from here we can just say our area is equal to, from here we can actually integrate. So when we're integrating, we are going to actually do the following. So we're going to have the integral of cosine x. The integral of cosine x is equal to sine x, positive sine x. And this would be plus cosine 2x over 2. That's the integral of sine 2x. Okay. And then this is within the interval of x is equal to 0 until x is equal to pi over 6. And here, we're going to add this with the other part, which looks something like this. So let me make it a little bit higher. So we're going to have the integral of sine 2x, which is minus cosine of 2x over 2, and we're going to have it with it should be minus, and we have sine of 2x. Oh, sorry, it's sine of x. I was thinking about the other thing. And this is within the interval of pi over 6 and x equals to pi over 2. Okay, so there we go. And now if we were to evaluate the following, we would actually, let me write it here, the area is equal to, now we're just going to evaluate, it's going to be sine of pi over 6. So actually, let me do it like this. If we plug in pi over 6 into sine of x, we get an output of a half, right? So we get a half. And when we plug in pi over 6 into cosine 2x over 2, we are going to get an output of a quarter. So that's going to be plus 1 over 4. And this is going to be minus, right? Because now we need to deal with the x equals 0. Note that sine of 0 is equal to 0. And cosine of 2 times 0, which is just going to be cosine of 0, which is 1, and 1 over 2, that's just going to be equal to a half. Okay, and then here we are going to add it, or actually let's subtract it. Why are we subtracting it? I'm going to take out the negative as a common factor, right? So when I take it out as a common factor, then note I'm just going to have a minus here. Okay, so from here we're going to work with those brackets. So it's going to be we're going to treat these as positives. So here it's going to be cosine of 2 times pi over 2, which should give us negative a half. Okay, and we would have positive sine of x of pi over 2. Let's say sine of pi over 2, that's just going to be equal to positive 1. Here we're going to subtract it with when we take this interval, or this part of the interval, which is pi over 6, and therefore we're going to be having, when we plug pi over 6 into all of this, we will actually get an answer of 1 over 4. And when we plug in pi over 6 into sine of x, we will be left with positive a half. And there we go. So from here, we're just going to evaluate the area. So this section here on the top, right? This section here on the top is going to give us an answer of 1 over 4. Okay. And then the section at the bottom, which is this one over here, right? So we're going to subtract it with that one there. We will get something such as negative 1 over 4. And this is just going to give us 1 over 4 plus 1 over 4, which is just going to be 2 over 4. And therefore we are left with an area of a half. Let's move on to the next question. Okay, and the last question here, we have something a little bit more different. You can see the question is a little bit shorter, but that's not really the difference. We need to find the area between the closed region of the curves, right? So they give us these two curves. They don't give us any interval. Bismillah. That's what we have. That's the question. So basically what's happening here is we need to do the same procedure. We need to find the points of intersection, which is between these two curves. Then we need to be able to sketch the function, the two functions on the same set of axes. And then if we are able to do that, we can find this so-called closed region that they're looking for. So let's just start off like that. So we'll find the point of intersection. We don't need to write it down. Just write down 3 over 2x squared equals to x cubed. There we go. They intersect at that point. We are trying to find those coordinates. From here, we can't divide both sides by x squared because x could be equal to 0. Otherwise, it'll be like dividing by 0. But what we can do is we can take this over. The 3 over 2x squared. So 0 is equal to x cubed minus 2 over 3. Well, it's 3 over 2. I do not want to have the wrong solution here again. I didn't re-record it. No, don't worry. Then we're going to have 0 is equal to, we can take it a common factor of x squared over here, such that we are left with x squared into x minus 3 over 2. Okay, and therefore, we have x values of x is equal to 0, coming straight from this parentheses over here, or we have x is equal to 3 over 2. Okay, so clearly, because there's no shifts, vertical shifts within these functions, we can see that they actually intersect at the origin. Kind of makes our life easier to understand. I mean, to understand our life, that's crazy. It kind of makes everything easier to understand, okay? But what we note here is we have another value, which is 3 over 2. We need to know what the y value is going to be. And how are we going to do that? Well, let's look at that. When we have y is equal to, let's use x cubed because it's better. If we have y equals x cubed, we plug in x equals to 3 over 2, and we cube that, and therefore we're left with 27 over 8. Okay. 27 over 8, that should actually give us a value, according to what I have, is 3.375. So 3.375. The reason why it's good to know this is because you know where to place it on the Cartesian plane compared to other values. And now that we have the y value, we can just sketch the graph. Okay, we can sketch the functions. So therefore we have our Cartesian plane here, and then what we're going to do is the following. So from here, we can actually sketch our cubic function. So y, and this is x, whatever. Let's sketch our cubic function. Our cubic function would look something like this. So it would be something like this, and it would be something like this. Okay? And that is our y equals 2x cubed. And then our square function, our parabola over here would look something like this. It is positive, intersects here at the origin, and looks something like so. So it kind of intersects there, because that's why this whole process here was important. So now we already know there is a point of intersection, and it could potentially, it would actually be somewhere here and here. So it'd be at x equals to 0, and also at this point here. And what was that x value? It was 3 over 2. Okay. And we said that the y value connecting to x equals 3 over 2, according to what we have here, is 3.375 or 27 over 8. Okay. Cool stuff. And then from here, note the area between, the region that we actually have, the closed region, is actually this area here. Can you see that? Between 0 and 3 over 2. Isn't that pretty cool? And funny enough, you're probably going to ask this question. How do you know which function is actually higher than the other between the red and the black? So this is something cool to actually take into consideration. Now, obviously, I've done this example already, so I know red is going to be higher. And we already know that it's kind of narrower as well. But at the same time, we can actually test that. So let's just do this quick test, and I'm going to show you what I mean. We want to take any value between 0 and 3 over 2. Let's take 1. Let's say 1 is somewhere here. Okay. We're going to take x equals 1, and we're going to compare it, we're going to substitute it into both of the functions over here given. Okay. So let's plug it into y equals 2, 3 over 2, and then we're going to plug in 1. Okay, I chose 1 because it's the easiest we can work with. This y value is just going to be 3 over 2. But if we plug it into our other function, which is y equals x cubed, then note that we're going to have 1 cubed, which is equal to 1. Now, which one is higher than the other one? Well, we can clearly see that 3 over 2 is actually equal to 1.5, which is higher than 1. So therefore, our red function, it was taken from the equation of the red function, is actually higher than that, the other function. So it looks something like this. Over there, we would have, it should be 3 over 2 and 1. Okay, so something like that. And that's how you can also verify. It's another way. So something cool to take into consideration. So let's neaten everything up and let's solve the question. So now we need to create the area, the region. So the area is just equal to the integral from, what we say, from 0 until 3 over 2. That's where the closed region is. So it's from 0 to 3 over 2. Okay, and then it's of the functions, and which one is higher than the other one? Remember, we said the red is higher than the black one, and we know that the red one is 3 over 2 x squared. Well, and we're going to subtract it with x cubed, which is lower than that with respect to x. From here, we can just integrate, right? So therefore, we're going to be having the area, which is equal to, now we can do this, the integral of 3 over 2 times x squared. That is just going to be, just to avoid making any errors, we have 3 over 2 multiplied by the integral. That's going to be x cubed over 3 minus, right? Because remember, this is a constant. We don't really have to do anything with that. Minus, it's going to be x to the power of 4 over 4. And this is going to be within the interval of x equals to 0 and x equals to 3 over 2. Okay. And here, what we notice is that the 3's can cancel, such that we are left with the area is equal to x cubed over 2 minus x to the 4th over 4. And this is between 0 and 3 over 2. Okay, so here now the area is equal to, we can just do the evaluation. And note that when we plug in x equals to 0, it will just all give us 0. So therefore we can actually disregard x equals to 0. Okay, please note that when you are going to do this, you need to indicate to the lecturer or the marker that because when x is equal to 0, then you will get an evaluation of 0. So that's why you're disregarding it. So just let them know. So therefore, we'll only be plugging in 3 over 2. So here we'll be having 3 over 2 all cubed over 2 minus 3 over 2 to all raised to the power of 4 over 4. And then therefore, the area is just going to be equal to 27 over 64. And like I say, you can either say that or you can even just say square units. And there we go. There's our answer for the third question.